Hi guys, my name is Amul Jasper from CSE department. My topic for this AAT on computer networks is on checksum method. We will discuss about the introduction and the challenges and few other topics in this video. Foundations of error detections in digital communication. Checksums are redundancy-based mechanisms designed to detect accidental data corruption during transmission across unreliable channels. They operate by appending a computed value to the original data block, enabling the receiver to verify integrity through recomputation and comparison. Checksums are the redundancy mechanisms which is designed to detect uh, any corruptions in the transmissions across the network and across various unreliable channels. And also, they operate by appending computing value to the original data block, enabling the receiver to verify that the actual data is being sent by the user and etc. Unlike cryptographic hashes, checksums prioritize speed and simplicity over collision resistance, making them suitable for real-time network protocols. Unlike cryptographic hashes, checksums they always prefer speed and simplicity over complexity, and making the which helps in making them suitable for real-world applications and real-world network protocols. The fundamental trade-off lies between detection capability and computation overhead. Early checksums methods merged alongside ARPANET development, establishing baseline reliability standards for packet switched networks. Mathematical framework of checksum computation. There is a mathematical framework for this checksum computation which helps in more reliable and more simplistic way, avoiding the complexity nature. Checksums are typically computed as one of the complement sums of all data volts treated as fixed size integers, often 16-bit. Once complements arithmetic ensures end around carry format, where overflow bits are added back to the at least significant position. Let's say we have a binary number 10001, so only one starting and the ending is 1 and the remaining all are 0. So uh, one's complement in the sense we will add a 1 to the uh, we will add 1 to the binary number at last. So this notes as one complements method. The receiver verifies integrated by summing all received words, including the checksum. A result of all ones indicates no detected error. This approach leverages all arithmetic over JF to power n, providing algebraic structure for error pattern analysis. Internet checksum. RFC 107 specification and properties. Let's see what is RFC 1071. The Internet checksum remains widely used in Internet Protocol TCP and UDP headers due to its balance to efficiency and effectiveness. Its progress and processes data as a sequence of 16-bit big endian integers, padding odd length messages with a 0 byte. The algorithm exhibits invariance under reordering of 16-bit words, remaining its ability to detect certain structural errors. Despite this weakness, it detects all single-bit errors and most burst errors up to 16 bits in length with high probability. Hardware acceleration via carry save adders enables line rate computation even on legacy network interface controllers. Limitations and failures modes of simple checksum. Checksums fail to detect errors where multiple bit flips cancel out in the sum, such as two identical words being corrupted oppositely. Word reordering attacks can produce valid checksums for maliciously altered packets, compromising data authenticity and data integrity. They offer no protection against intentional tampering, distinguishing them fundamentally from cryptographic message authentication codes. Longitudinal redundancy checks (LRC) in short, and vertical party suffer from similar linear weakness, motivating more robust alternatives. Empirical studies show undetected error rates of approximately 1 in 16 million for random noise in 16-bit internet checksums. Cyclic redundancy check is also known as CRC, algebraic structure and polynomial encoding. CRC treats data as coefficients of binary polynomial, dividing it by a fixed generation polynomial over GF2. The remainder of this division forms a CRC value appended to the message for verification at the receiver. Generator polynomials are carefully chosen to maximize Hamming distance and detect common error patterns like single bit and burst errors. Common standards include cyclic redundancy check 32 used in Ethernet and ZIP, CRC 16CC ITT X.25, and CRC 64 ISO high intensity storage. The algebraic framework enables mathematical proof of detection capabilities based on polynomial degree and properties. CRC implementation techniques, table driven and bitwise optimization. Bitwise CRC computation processes one bit at a time using shift registers and conditional XOR operations with the generator polynomial. Table-driven methods pre-compute 256 entry lookup tables for bitewise processing, reducing per byte cost to a single table access and XOR. Modern implementations use slicing by end techniques that processes multiple bytes in parallel using SIMD instructions over or wider registers. Hardware CRC units in modern NICs and storage controller compute CRC at wire speed with zero CPU overhead. Optimized software libraries like zlib and Intel's ISAL leverage instruction set extensions for cryptographic grade performance. Fletcher and Alder checksums. Adaptive sums for streaming data. Fletcher checksums maintain two running sums, one cumulative and one of cumulative sums, enhancing sensitivity to word ordering and spacing. Alder 32 used in Zilip modifier Fletcher's approach with modulo prime arithmetic to reduce collision likelihood. These algorithms detect all single-bit errors and most word transpositions. They are computationally lightweight, requiring only addition and modulo operations, ideal for embedded and real-time systems. However, both remain vulnerable to draft, crafted collisions and unsuitable for security critical applications without adding safeguards. Hash-based checksums from MD5 to Blake 3 in network integrity. Cryptographic hash functions like SHA-256 and Blake 3 provide near certain error detection with negligible collision probabilities. Blake 3 leverages Berkeley trees and vectorized operations to achieve gigabyte per second throughput on modern CPUs. Trade-offs include increased header size and processing latency, limiting deployment to control plain or bulk data scenarios. Checksum offloading and hardware acceleration in modern NAS. TCP and ICP checksum offloading delegates checksum computation from CPU to network interface cards, reducing post-processing load. This introduces subtle bugs when virtualization or tunneling alters packets boundaries without updating offload checksums. Performance benchmark shows up to 40% of CPU reduction in high throughput servers. Emergency trends, network coding and integrated error detection. Network coding combines packets linearly at intermediate nodes requiring checksums that operate over encoded surfaces. Cross-layer designs integrate physical layer error indicators with transparent layer checksums for intelligent retransmission decision. Case study: Checksum Evolution Aeronautical Communication Protocols. Ionics networks like ARINC 2429 and AFDX employ CRC16, CRC32 for frame integrity in safe critical flight systems. DEVO 186C certification requires rigorous validation of checksum implementations, including fault injection and coverage analysis. Thank you.